Three-dimensional vectors, Level 1. In the previous videos, we reviewed the basics of two-dimensional vectors, also known as planar vectors. In the following series of videos, we will go over three-dimensional vectors, also known as vectors in space. The transition from planar vectors to vectors in space requires the addition of a third component in order to represent the direction that points along the z-axis of a three-dimensional coordinate system. For example, the position vector with an x component of 2 and a y component of 3 is represented in a two-dimensional coordinate system as follows. Now, if we wanted to represent this same vector in 3D space, we will need to add an additional component, in this case, the z component. For this particular example, the vector is going to be located on the xy plane, so it will have a z component of 0. So this vector will have an x component of 2 and a y component of 3, and a z component of 0. In the same manner, the following vectors would be located on the xz plane and yz plane, respectively. Notice that in each case, there is a component equal to 0. Any vector in R³ that has one component equal to 0 will lie on a coordinate plane because they resemble two-dimensional vectors. In general, a vector located in space will have three components and are denoted by ordered triples as opposed to ordered pairs. If two components of a vector in R³ are equal to 0, then the vector will lie along a line. For example, the following vectors each have two components equal to 0, and they lie in the direction of the x-axis, y-axis, and z-axis respectively. Just like two-dimensional vectors can be represented by using the standard unit vectors, also known as standard basis vectors, we can also use the same notation to denote vectors in space. In this case, we will use the unit vector I hat, j hat, and the unit vector k hat, which represents the unit vector that points along the z-axis. Any vector in space can be represented by a scalar multiple and sum of the unit vectors. For example, the vector with components 1, 2, and 3 can be represented as I plus 2j plus 3k. If a vector has 0 for every single component, it is referred to as the zero vector, and can be represented by a single point. Now, if a vector is not in standard position, with the tail located at the origin, and it is instead represented by 2 points in space, like point P for the tail or initial point, and point Q for the head or terminal point, then we can find the component form of vector v by subtracting the coordinates of the initial point from the coordinates of the terminal point, as follows. Lastly, many of the properties for two-dimensional vectors also apply to three-dimensional vectors. For example, two vectors are still equal if and only if the components of both vectors are equal. In other words, vector u is equal to vector v if and only if the x components, y components, and z components are equal. Two non-zero vectors are still parallel if there is some scalar c such that vector A equals the scalar c times vector b. In other words, the x, y, and z components of vector A are a constant multiple of the x, y, and z components of vector b, respectively. The length or magnitude of a vector in space is calculated similarly to planar vectors. The only difference is that we include the third component into the expression, as follows. This is essentially the Pythagorean theorem in 3 dimensions. To find a unit vector in the direction of a vector v, we simply take the components of vector v and divide it by the magnitude of vector v, as long as vector v is not the zero vector. Lastly, the properties of vector addition and scalar multiplication given for planar vectors are also valid for vectors in space. For vector addition, we simply add the vectors component-wise. And when multiplying a scalar by a vector, we simply multiply this scalar to each of the vector's components. Alright, let's go over some examples and illustrate how to solve various problems involving three-dimensional vectors. Find the component form of vector v and write the vector using standard unit vector notation. Sketch vector v with its initial point at the origin. Alright, here we are given the initial and terminal points of a vector. In order to find the component form of vector v, we simply need to subtract the coordinates of the initial point from the coordinates of the terminal point. Doing that, we obtain the following values for the components of vector v. Next, we go ahead and write this vector using the standard unit vectors. This is a pretty straightforward process, since each of the components corresponds to I, j, and k respectively. Doing that, we obtain the following expression. Finally, we need to sketch this vector in standard position. So we start at the origin and use the components to plot the coordinates of the terminal point, just the way you plot points in a three-dimensional coordinate system. So, we go ahead and move 4 units along the positive x-axis, and move 5 units along the negative y-axis, and move 2 units along the positive z-axis. Then, we go ahead and join these 2 points with a directed line segment, as follows. Alright, let's go over the next example. Find the component form and magnitude of the vector, with initial point 4, -5, 2, and terminal point -1, 7, -3. Then, find a unit vector in the direction of this vector. Alright, similar to the previous example, we are given the initial and terminal points of a vector in 3 dimensions. Let's call this vector vector v. So we go ahead and subtract the coordinates of the initial point from the coordinates of the terminal point, as follows. This expression represents the components of vector v. Now let's find the magnitude or length of vector v. This requires an application of the Pythagorean theorem in 3 dimensions. Substituting the components into the expression and simplifying, we obtain the square root of 194 as the magnitude of vector v. Alright, now that we found both the component form and the magnitude of vector v, we can go ahead and find a unit vector in the direction of vector v. We find this unit vector by simply dividing each of the components of vector v with its magnitude. Doing that, we obtain the following components for the unit vector in the direction of vector v. You can easily verify that it's a unit vector by computing the magnitude and checking that it is equal to 1. Alright, let's go over the final example. Vector v has components equal to 1, -2/3, and 1/2. The initial point of vector v is 0, 2, and 5/2. Find the terminal point. Here we're given the components of vector v and its initial point. We are asked to find its terminal point. We can figure out the terminal point by using the expression for finding the components of a vector and working backwards. We know that if we were to take the initial point and subtract each coordinate with the coordinates of the terminal point, we should obtain the component form. With this setup, we can see that finding the terminal point essentially requires us to solve for the x, y, and z coordinates of the terminal point. Isolating each expression and solving for the coordinate point, we obtain 1, 4/3, and 3 as the coordinates of the terminal point. Alright, in our next video, we will go over slightly more challenging examples. 3-dimensional vectors, Level 2. In this video, we will go over slightly more challenging examples that require the application of various concepts associated with 3-dimensional vectors. Alright, let's go ahead and jump straight into the first example. Find vector z given that vector u equals 1, 2, 3, vector v equals 2, 2, -1, and vector w equals 4, 0, -4, where vector z equals 5u minus 3v minus 1/2 w. Alright, in this problem, we need to use the properties of vector addition to find the sum of these vectors. We first need to carry out a scalar multiplication for vector u, v, and w. So let's go ahead and carry out the scalar multiplication first. Next, it is just a matter of adding or subtracting the vectors component-wise. Doing that and simplifying, we obtain the final answer equal to -3, 4, and 20. Once again, notice that vector arithmetic in R cubed is essentially the same as in R squared. Alright, let's move along to the next example. Determine which of the vectors is or are parallel to vector z, where vector z equals 3, 2, -5. Alright, recall that two vectors are parallel if one vector is a constant multiple of the second vector. For this problem, we need to find or show that there exists a scalar that generates vector z when multiplied by the vectors shown below. For the first vector, we are essentially trying to show that vector z equals c times vector v. We can go ahead and break apart the vector equation into its three components as follows. Then, we go ahead and solve for the constant c. Notice that in all three components, we obtained the same constant. This means that we can multiply vector v by the scalar -1/2 and obtain vector z, meaning that vector v is parallel to vector z. For the second vector, we do the same and break apart the vector equation into components and solve for c. Doing that, we obtain the following values for c. Once again, notice that every component has the same value for the scalar. This means that vector w is also parallel to vector z. Lastly, we do the same for vector u and break apart the vector equation into separate components and solve for the scalar, obtaining the following. Notice that the x and y components are the same, but the z component is negative. We need all three scalars to be the same for all components, including the sign. Since this scalar does not match the rest of the scalars on the other components, we can conclude that vector u is not parallel to vector z. So vector z is parallel to vector v and vector w only. Alright, let's move along to the next example. Use vectors to determine whether the points A, B, and C are collinear. Alright, let's go ahead and plot these points so we can get a visual for this problem. We are asked to show that these 3 points lie along the same line. In other words, they are collinear. We can show this by using vectors by first assuming that they are collinear and break the line into 2 pieces, or in this case, 2 vectors, making sure that we use a common point for both vectors. In this case, let's go ahead and find the components of the vector represented by points A and B and the vector represented by points A and C. To find the components of the first vector, we simply subtract point A from point B and obtain the following for the components of vector AB. And then we do the same for vector AC and subtract point A from point C, obtaining the following for the components of vector AC. Now, if both of these separate vectors lie in the same line, they should be parallel to one another. So we need to show that they are a constant multiple of each other. So we go ahead and set up our vector equation, and by inspection, we see that we can obtain vector AB by multiplying vector AC by -2. Since both of these vectors are parallel, and they pass through the same point, in this case, point A, we can conclude that they are collinear. Alright, let's try the next example. Find the magnitude of vector v, where v equals -4i plus 3j plus 7k. Alright, here we have a vector written using the standard unit vectors. Recall that this form is very similar to the component form of a vector. In this case, each of the scalars represents the x y, and z components respectively. So to find the magnitude, we simply use the Pythagorean theorem in 3 dimensions. Doing that, and simplifying, we obtain the square root of 74 as the final answer. Alright, let's try the next example. Determine the value of c that satisfies the equation the magnitude of scalar c times vector u equals 4, where vector u equals -I plus 2j plus 3k. Alright, we want to find the values of scalar c that satisfies the vector equation. We are given vector u written with unit vectors, so we can go ahead and rewrite this expression into its component form as follows. Next, let's go ahead and substitute the component form of vector u into the vector equation. Then we go ahead and multiply scalar c into each of the components of vector u as follows. Notice that up to this point, the vector equation is essentially stating that the magnitude of this vector should equal 4. So we go ahead and find the expression for the magnitude of this vector by using the Pythagorean theorem in 3 dimensions. Simplifying the vector equation, we obtain the following. Now it is just a matter of solving for the scalar c. So we go ahead and square both sides, solve for c squared, and then take the square root of both sides. Doing that, we obtain 2 solutions, positive and negative, the square root of 8/7. Let's go over the final example. Find a vector v with magnitude of 3/2 and in the same direction as vector b, where vector b equals 2, -2, and 1. Alright, here we're asked to generate a vector that has a magnitude of 3/2 and points in the same direction as vector b. We first need to extract the unit vector from vector b. This way, we can obtain a vector that has the direction of vector b and will have a magnitude equal to 1. This way, when we multiply it by a scalar, only the length of the vector will change, keeping the same direction in the process. Let's start by finding the magnitude of vector b. Simplifying the expression, we obtain 3 as the magnitude of vector b. Next, let's go ahead and find the unit vector. So we take the components of vector b and divide them by the magnitude of vector b. Doing that, we obtain the following components for the unit vector. Now it is just a matter of multiplying this unit vector by the magnitude of vector v. Since the unit vector points in the same direction as vector b, it is just a matter of scaling the vector to the appropriate magnitude, in this case, 3/2. Doing that, and simplifying the expression, we obtain 1, -1, and 1/2 for the components of vector v. This vector has a magnitude of 3/2 and points in the same direction as vector b. Okay, in our next and final video on 3-dimensional vectors, we will go over some more challenging examples. 3-dimensional vectors, Level 3. In this final video on 3-dimensional vectors, we will go over 4 examples. The last example will be a static equilibrium problem in 3 dimensions. Alright, let's go ahead and take a look at the first example. Sketch vector v and write its component form. Vector v lies in the yz plane, has a magnitude of 2, and makes an angle of 30 degrees with the positive y-axis. Alright, since this vector lies on a plane, it will have one component equal to 0. In this case, the x component will be equal to 0. Now, to determine the value of the other components, we can go ahead and use right triangle trigonometry to find the y and z components of the vector. According to the problem, vector v makes an angle of 30 degrees with the positive y-axis. This means that it can form 2 separate angles, positive 30 degrees and negative 30 degrees. So we have 2 solutions that satisfies the conditions of the problem. Now that we have identified our vectors, it is just a matter of using the 30, 60, 90 special right triangle to determine the values of the y and z components. Doing that, we obtain the following expression. Now, for the y component, cosine of positive 30 degrees and cosine of negative 30 degrees yield the same value, and when multiplied by the magnitude, it would reduce to the square root of 3. But for the z component, sine of 30 degrees and sine of negative 30 degrees yield different answers that differ only by negative sign. So taking this into account and simplifying the expression, we obtain positive and negative 1 for the z component. So the components of the vectors that satisfy the conditions of the problem are equal to 0, square root of 3, and positive negative 1. Alright, let's try another similar problem. Vector v lies in the xz plane, has a magnitude of 5, and makes an angle of 45 degrees with the positive z-axis. Similar to the previous example, let's go ahead and make a sketch of the problem. Notice that we can also form two separate vectors that make an angle of 45 degrees with the z-axis. So this problem will also have two solutions. Since the vectors lie in the xz plane, the vectors will have a y component equal to 0. At this point, it is just a matter of using right triangle trigonometry and find the components of each vector. If we change our point of view and focus on the xz plane, we would see the following. Now, if we use the standard conventions for measuring angles, the first vector would make an angle of 45 degrees relative to the positive x-axis, and the second vector would make an angle of 135 degrees relative to the x-axis. Using these values for the angle, we can compute the values of each component by using the ratios of a 45-45-90 special triangle and then multiply by the magnitude of the vector. Doing that, we obtain the following for the first vector. 5 times the square root of 2 over 2, 0, and 5 times the square root of 2 over 2. For the second vector, the values of each component will be the same, but the x, or I hat component, will be negative, since cosine of 135 degrees yields a negative value. Alright, let's go over the next example. Use vectors to find the point that lies 2/3 of the way from point P to point Q. Alright, let's go ahead and plot these points to get a graph that we can work with. We are asked to determine the coordinate point that is 2/3 of the way from point P to point Q. We can determine this by first finding the component form of the vector represented by the points P and Q. So we go ahead and subtract the initial point from the terminal point. Then we simplify the expression, obtaining -3, -6, and 3 for the components. Next, let's go ahead and scale this vector by a factor of 2/3. Doing that, we obtain the following components. Now, this component essentially tells us the difference between point P and the point that is 2/3 away from point P. So all we need to do is to take point P and add the components of the scaled vector. Doing that, we obtain the final coordinate equal to 2, -1, and 2. Alright, let's end the video with the final example. Find the tension in each of the supporting cables in the figure below if the weight of the crate is 500 newtons. Alright, here we have a static equilibrium problem in three-dimensional space. The concepts of static equilibrium are the same. The sum of all the forces acting on a body has to equal 0. For this particular problem, we have a crate that is hanging from 3 ropes, attached at various parts, relative to a three-dimensional coordinate system. We are given the coordinates of points A, B, C, and D. Alright, the first step is to find an expression for each of the forces that are acting on point A. This is going to include 3 tension forces, 1 for each rope, and the weight of the box. Let's first find an expression for each of the 3 tension forces. Let's label 3 separate vectors by using the points that are provided to us. These forces will represent the tension force along point A and point B, along point A and point C, and the tangent force along point A and point D. Next, we need to write the component form for each vector. The only problem is that we currently have no idea what the magnitude of each tangent force is, but we are able to at least find the components for the direction of each of the tangent force by using the coordinate points provided to us. The component form of the force from point A to point B can be found by taking point A and subtracting it from point B. The component form of the force from point A to point C can be found in a similar fashion, and the force from point A to point D will also be found in the same way. Simplifying the expression, we obtain the following for the direction of each tangent force. Now, we currently have no idea what the magnitude of the force for each tension is equal to, but we know that if we were to take the direction of each tangent force and multiply it by some scalar c sub 1, c sub 2, and c sub 3, for each of the forces, we should be able to obtain the component form for each tangent force. We will use these constants along with the direction of the ropes to temporarily represent the tension forces. We will also express the weight of the crate as a force with only one component, in this case, negative 500 newtons along the negative z-axis. Now we can go ahead and find the sum of all the forces and set it equal to 0, as follows. Next, we need to extract 3 separate equations, one for each component. For the x component, we obtain the following equation. For the y component, we obtain the following. And for the z component, we get the following expression. Now we are face to face with a system of equations. So we have 3 unknowns and 3 equations. We should be able to find the solution for each of the constants. Using the first equation, we go ahead and solve for c sub 2. And using the second equation, we go ahead and solve for c sub 1. This allows us to substitute these constants into the third equation, reducing it into an equation with a single variable. From here, it is just a matter of collecting like terms and solving for c sub 3. Simplifying the expression, we obtain the following value for c sub 3. Now we go ahead and solve for c sub 1 and c sub 2. Doing that, we obtain the following values. The last step is to go back to our expressions representing the tension force for each rope and substitute these scalars and then multiply it by each rope's direction vector. This generates the component form for each tension force. And finally, all we need to do is to find the magnitude of each tension force by using the Pythagorean theorem in 3 dimensions. Approximating the magnitudes, we obtain the following values for each of the forces. Alright, and this ends the video series on 3-dimensional vectors. In our next series of videos, we will go over a new vector operation called the dot product.